Hey guys, today we're going to be taking a look at modulus, part 3, what is the modulus of a complex number? And hence the part 3, you're currently in the third video of my complex number series. In the first video we talked about what are complex numbers and just kind of the form of complex numbers. In the second video we talked about conjugates of a complex number, and in this video we're going to talk about the modulus of a complex number. So without further ado, let's get started. Alright, so let's just get straight into it. The modulus of a complex number, and the complex number is in the form of z equals a plus bi, is this, and this is basically how you denote the modulus of a complex number. In this case, the complex number is z, so we have this kind of straight bracket or like straight lines around this z, which is a complex number, and that represents the modulus of a complex number, which is equal to square root of a squared plus b squared, which is further equal to, or not further equal to, I should say, like a different way you could write it, and that would be square root of the real part of z squared. The real part of z, we know that's just a over here, plus the imaginary part of z, and we know that that's b. So basically this and this are the same, they're just written in two different formats. Whatever helps you remember it better, I suggest you stick with that. But ultimately they're the same. So let's try a few problems relating modulus to complex numbers. Alright, so now let's take a look at some problems. The first problem is z1 equals 3 minus 4i. And pause the video right now and give this problem a go if you know how to do it. Alright, so I'm going to walk through the solution with you. We're supposed to find the modulus of a complex number, and we have the rule right here. So by looking at this and by looking at this problem, this complex number, we should be able to find the modulus. So first, let's find the modulus, and we don't denote it as this, I don't know what you call it, these straight lines, z1, and then straight line closed, that's the modulus. That's how we represent a modulus. And that is equal to square root, over here we see it's equal to square root a squared plus b squared. In this case, 3 is a, and minus 4 is b. So we have 3 squared plus, and then b is minus 4, so minus 4 squared. Let's solve this. We get 9 plus 16, which is equal to square root 25, which is further equal to 5. So the modulus of this complex number 3 minus 4i is 5. Alright, let's move on to the next problem. The next problem is z2 equals minus 5 plus 2i. Once again, feel free to pause the video and give this problem a go. Alright, so once again, same thing as before. Let's find the modulus. So we get z2 is equal to square root a squared plus b squared. A in this case is minus 5, b in this case is 2. So we get minus 5 squared plus 2 squared. This is equal to 25 plus 4, which is equal to square root 29. So square root 29 is the modulus, of z2 equals minus 5 plus 2i. Now let's move on to this third problem. z3 equals, 1 plus square root minus 3. Once again, feel free to give this problem a go. Alright, so now you might be thinking, well, where's the I, right? Well, actually, we have to introduce the I, right? We know that I is nothing but square root negative 1. I is nothing but square root of negative 1. So that's, if we split this into z3 equals 1 plus square root negative 1 times square root 3, we can split square root negative 3 into square root negative 1 times square root 3, right? That's perfectly valid. So then we get z3 is equal to 1 plus square root 3i. I being outside the square root because we know I is square root of negative 1. So now we have introduced an I. Now we can solve it how we solved the first and second problems. So we can simply do z3 equals square root, a here is 1, so 1 squared, plus square root 3 squared, because square root 3 is b. We get square root 1 plus 3, which is 4, square root 4 is 2, and therefore 2 is the modulus of the complex number 1 plus square root minus 3. Alright, so hopefully you got like a gist of how to find the modulus of complex numbers from over up here. It's nothing too, I hope it's nothing too hard. Essentially all you have to remember is this formula. And it's not really a formula, it kind of comes to your mind the more problems you do. But essentially the modulus of a complex number is square root a squared plus b squared, or in other words, square root the real part of z squared plus the imaginary part of z squared. And now let's move on to the properties of modulus. And like we did in part 2, we had properties of conjugates, and mind you, there are a lot of properties, like 10 or 11 for modulus. So it can be confusing at first, especially if you're mixing and matching properties of modulus with properties of conjugates. So if you're planning to do more questions on modulus or conjugates or just complex numbers in general, I suggest you write these properties down, which I'm going to go over. But first, I'm going to handpick some of the properties which I think are the most useful, and we're going to prove them together so we know that, okay, this property is actually true. Alright, so I started off with hopefully the easiest property of modulus to prove, which is if the modulus of z is equal to 0, then z, which is the complex number, is equal to 0. And an example is the real part of z is equal to the imaginary part of z is equal to 0. So how do we prove this? Well, we know that the absolute value of z, if z is, let's say, a plus bi, the absolute value of z is going to be square root a squared plus b squared, right? That's what we learned above. So now we have square root a squared plus b squared. But they're saying this is equal to 0. So that is equal to 0. The only way this could be 0 is if both a and b are 0. Then only this is true. So what does that mean? Okay, a and b are 0. Let's plug it in this complex number. That's z equals 0 plus 0i, which is z equals 0. So z equals 0 and z equals 0. What does that further mean? Well, if z equals 0, we know that the real part of z, is 0 also. The real part of z is 0. And that's because we know that the real part of z in this case is a. And we know that a is 0 from over here. So that's saying the real part of z is 0, and the imaginary part of z is also 0. So hence this property is proved. Now off to the second property of modulus. The second property of modulus is z times z conjugate equals the absolute value of z squared. And in part 2 we discussed a lot about conjugates, so if you don't know what a conjugate is, then I suggest you go and watch that video. But for now, I'm assuming you know what a conjugate is, so let's start proving this. So let's assume, once again, that z is equal to a plus bi. Therefore, the conjugate, this is the conjugate of z, the conjugate, is equal to a minus bi. So we have the complex number z and the conjugate z, the conjugate of z, which is a minus bi. So this is, the left hand side is asking us to multiply those together, so let's do that. We have a plus bi times a minus bi. So that's a squared minus b squared, I squared. We know I squared is simply minus 1 times minus b squared is plus b squared. So we have the left hand side, z times z conjugate is equal to a squared plus b squared. And let's see if that's what is also the right hand side. So the right hand side, we know it's this. So let me just write it here. Let's first solve the modulus of z. From up here, we saw that the modulus of z is square root a squared plus b squared when our complex number is a plus bi. So that's basically square root a squared plus b squared, and this is only for the modulus of z, but the modulus of z is being squared, so this is squared. This squared and the square root cancel out, you're left with a squared plus b squared, and what do you know? The left hand side is equal to the right hand side. Therefore, this property is true for all complex numbers. Alright, so our second property, or third property I should say, of modulus is modulus of z1 times z2 is equal to the modulus of z1 times the modulus of z2. And once again, feel free to pause the video, try to solve this on your own. Alright, so hopefully you gave that problem a go, but if you didn't, I'm going to go over the solution right now. So once again, let's assume z1 is a1 plus b1i. It's just a complex number. And z2 is equal to a2 plus b2i. So let's solve the left-hand side. Let's try to prove that the left-hand side is equal to the right-hand side by substituting actual values like z1 is a1 plus b1i and z2 equals a2 plus b2i. So the left-hand side is absolute value of z1 times z2. So z1 is a1 plus b1i, and z2 is a2 plus b2i. Absolute value of that. Now let's multiply those. That's a1 a2 plus a1 b2i plus b1 a2i plus b1 b2i squared. Let's take out the I in these two terms, so we get a1 a2. We know that I squared over here is just minus 1. This is equal to minus 1, so that's basically minus b1 b2. Let's take the I out from these two terms, so we get b1 a2i. So I just took out the I, and is that correct? Okay, so let me get another page. Now we have this modulus going on, but once again it's the same exact procedure. Instead, let's try to use this one. This one and this one are the same, but for making it a bit more sense, let's use this one. It's saying the real part of z squared plus the imaginary part of z squared. The real part of z is this, and the imaginary part of z is this. So that's basically saying square root of the real part of z, which is a1, a2 minus b1, b2 squared, plus the imaginary part of z squared. Imaginary part of z is a1, b2 plus b1, a2 squared. Whoops. Alright, and now we are still on the left-hand side. So I'm just gonna stop here right now. Let's say that this is the LHS, the left-hand side. Let's start solving the right-hand side. The right-hand side, let me just copy this down here. Whoops. Alright, so let's solve the right-hand side, the right side. Once again, z2 is a1 plus b1i. z2 is a2 plus b2i. Let's find the modulus of this. That is just a1 squared plus b1 squared times a2 squared plus b2 squared. These are square roots, so we can multiply them. So we get square root a1 squared a2 squared. On second thought, let me write it in a bit easier way. So we have square root a1 squared plus b1 squared times a2 squared plus b2 squared. Close that bracket. Simplifying this, we get a1 a2 squared plus a1 b2 squared plus b1 a2 squared plus b1 b2 squared. And this is the right hand side. So we see that the right hand side is not equal to the left hand side, but we can simplify the left hand side. So let's do that right now. I'm just going to erase the top part because we don't need it anymore. So now on to simplifying this. So we get, okay, equals. Let's expand this whole thing. Yes, it's a lot of math, but that's all right. So we get a1 a2 squared plus b1 b2 squared minus 2a1 a2 b1 b2. And let me erase this. And that is, we're solving this part now, so we get plus a1 b2 squared plus b1 a2 squared plus 2a1 a2 b1 b2. This and this cancel out. Can we cancel out anything else? No, we cannot. So rewriting this, we have a1 a2 squared plus b1 b2 squared plus a1 b2 squared plus b1 a2 squared. So there we go. And now we see that the left-hand side, let me highlight this, the left-hand side, this over here, is actually equal to the right-hand side. So therefore, this property is true for all complex numbers. Alright, so here are the list of the properties of modulus, and yes, it is a lot. There are 10 properties of modulus, and the ones underlined in black are the ones we went over, but essentially you could prove any of these properties of modulus just like we did, assuming that z is equal to a plus bi, or maybe z1 is equal to a1 plus b1i, or z2 equals, you get the idea. What I'm trying to say is that it's not too hard to prove these. You just assume that z is a complex number in terms of a and b. As long as you know just simple algebra and what the real number of z is and the imaginary number of z is, you should be fine. But one thing I want to note is that it comes down to, it comes down to this property and this property. So you see that this property, they kind of have something in common. For example, we actually proved this one. It says that the modulus of z1 times z2 is equal to the modulus of z times modulus of 2. And this one says modulus of z1 over z2 equals modulus of z1 over modulus of z2, where z2 is not 0. And what you may have noticed is that you don't find any property which is labeled such as z1 plus z2 is equal to z1 modulus plus modulus of z2. Or you don't find any property that's z1 minus z2 equals the modulus of z1 minus z2 equals the modulus of z1 minus the modulus of z2. That's because if you apply these properties, they are wrong. They are wrong because the left-hand side does not equal the right-hand side in any of these properties. So if you were to apply this, you would get the answer wrong. You will not get the correct complex number in any of the complex number problems. So it is very crucial to remember that the properties of modulus, in terms of kind of this type of property, it only applies in multiplication and division, not in addition or subtraction. Conjugates, those are a different thing, kind of, because in conjugates, this would be true, but that's only for conjugates. In addition, conjugates also have this property and this property. So they have all the properties. They have addition, subtraction, multiplication, and division. But for modulus, what we're doing here, it only has the multiplication and division. So I just wanted to point that out because it is a really crucial factor of properties of modulus, and people can get confused if we're talking about modulus or conjugates, and they may apply the wrong formula or the property. So I just wanted to get out of the way. And next, you may have seen these ones. They're really, really long, but overall, it's kind of, once again, same thing. Just assume z is a complex number. And these three properties have something to do with each other. So you see that this is z1 plus z2 modulus squared. This is z1 minus z2 modulus squared. This is z1 plus z2 modulus squared plus z1 minus z2 modulus squared, and that's equal to that. So yeah, so if you want to prove any of these properties, I highly encourage you to. It's just a matter of maybe 2 or 3 minutes. It's not going to be the end of the world if you make sure these properties are true. I'm hoping these are true. So yeah, that is modulus part 3. What is the modulus of a complex number? And I will see you guys in part 4. Bye.